Hello friends, welcome back. Let us solve KSET 2016 Physical Science Paper 2 remaining 25 questions. For a particle confined in a one-dimensional box of length A, the energy levels for a particle of mass m are given by. We know that energy of a particle in 1D box is given by E is equal to h cross square k square upon 2m, where k is the wave vector given by n pi by l. L is the width of the box. Here it is equal to A. Therefore, E is given by h cross square n square pi square divided by 2m A square. Therefore, option A is correct. Let Lx, Ly and Lz denote the Cartesian components of angular momentum. Study the following statements. First statement is Lx, Ly and Lz do not commute with each other. Lx, Ly, Lz commute with L square. The commutator of Lx and Ly depends linearly on Lx and Ly. Then commutator Lx, Ly with Lz is equal to 0. Choose the correct statement. Two components A and B are said to be commute. Then commutator A and B should be is equal to 0. Then only we will say that they commute with each other. So here in first statement it is given that Lx, Ly, Lz do not commute with each other. We know that commutator Lx, Ly is equal to IH cross Lz. Similarly, Ly, Lz is IH cross Lx. Lz, Lx is equal to IH cross Ly. From these three, we can say that Lx, Ly and Lz do not commute with each other because their value is not is equal to 0. Therefore, statement 1 is 2. I will go to statement 2. That is Lx, Ly and Lz commute with L square. So we know that Lx L square is equal to Ly L square is equal to Lz L square. That is equal to 0. Therefore, Lx, Ly, Lz commute with L square. That is also true. Third statement is the commutator of Lx and Ly depends linearly on Lx and Ly. But we know that commutator of Lx to Ly is IH cross Lz. That means commutator Lx, Ly depends only on Lz, not on Lx and Ly. Therefore, this is not true. Now we will consider fourth statement. Lx, Ly, Lz. So we know that Lx, Ly is IH cross Lz. Then commutator of any quantity with itself is always 0. Therefore, IH cross into 0 is 0. Therefore, this is also true. So, statement 1, 2, 4 are correct. 3 is false. Option C is correct also. A beam of particles having mass m. So, beam of particles having mass m and velocity v is incident on a slit of slit width a. Then the approximate spread of the particles on a screen kept at a distance L. So, slit to screen distance here L. So, we have to find approximate spread of the particle delta x. The spread of the particles is same as fringe width given by lambda e by small d, where d is the slit to screen distance, and small d is slit width. So here delta x can be written as lambda into capital D means L, small d means A, slit width is A. From de Broglie equation we know that lambda is equal to h cross by p. So p is mv into linear momentum into A. Therefore, spread of the particles on a screen is given by h cross L upon mva. Option B is correct. Fourfold degeneracy in the excited state n is equal to 2 in hydrogen atom can be partially removed by. So we know about Stark effect. It is the splitting of energy levels in presence of electric field. So if energy level splitted in presence of magnetic field, then we will call it as Zeeman effect. So here in Stark effect, the splitting of energy levels takes place in presence of electric field. So here fourfold degeneracy is partially removed. Therefore, it can be partially removed by application of weak electric field. Two successive application of an operator P on the function leaves the function unchanged. The eigenvalues of the operator are. So given that two successive application of an operator P on the function, if you consider function as psi, then it leaves the function unchanged. That means P square psi is equal to psi. So it is eigenvalue equation. That means eigenvalues of P square is equal to 1. Therefore, eigenvalues of P are less than minus 1. Option C is correct. A system has an unperturbed Hamiltonian in energy units given by 15, 0, 0, 0, 0, 3, 0, 0, 0, 0, 3, 0, 0, 0, 0, 3. The unperturbed energy eigenvalues of the system are. Here unperturbed Hamiltonian H0 is given. So it is a diagonal matrix. And we know that for any diagonal matrix, eigenvalues are its principal diagonal elements. Therefore, here principal diagonal elements are 15, 3, 3, 3. Therefore, the unperturbed energy eigenvalues of the system are 15, 3, 3, 3. Option A is correct. The Hamiltonian of the system is given by H is equal to 1, 0, 0, 0, 0, 8, 0, 0, 0, 0, 3 minus 2 lambda, 0, 0 minus 2 lambda, 7, where lambda is a small parameter. By decomposing the same as H is equal to H0 plus P, H0 plus HP, the eigenvalues of unperturbed Hamiltonian H0 can be obtained. The eigenvalues of H0 are. Here H is given, and it is given that H0 plus H is equal to H0 plus HP. You can write it as 1, 0, 0, 0, 0, 8, 0, 0, 0, 0, 3, 0, 0, 0, 0, 7 plus, if you consider this as H0, plus 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, minus 2 lambda, 0 0 minus 2 lambda 0 is a Hp. So it can be decomposed as H naught plus Hp. Since H naught is a diagonal element, the energy eigenvalues of H naught are 1, 8, 3 and 7. Option C is correct. The ground state energy for a particle in a box is 1.25 electron volt. If 3 particles each having half spin are introduced in the box, then the total ground state energy of the system will be. So for a particle in a box, energy is given by En is equal to n square pi square h cross square divided by 2m a square. And here it is given that energy for a particle, ground state energy for a particle in a box is 1.25 electron volt. That is E1 is pi square h cross square divided by 2m a square. That is equal to 1.25 electron volt. Then if 3 particles each having spin half are introduced in the box. So there is a box. If 3 particles each having spin half means only 2 particles can accommodate. So there are 3 particles. 2 particles are in state E1 and 1 particle in E2. Therefore total energy is given by E total is equal to 2 into E1 plus 1 E2. 2 into 1.25 electron volt plus E2. E2 means, so 2 square. E2 is 2 square into E1. That is 4 E1. It is 2.50 plus 4 into 1.25. 1.5 plus 5. That is 7.5 electron volt. Therefore, option D is correct. Uncertainty in velocity for an electron in a 1 angstrom radius orbital in which the positional uncertainty is 1% of the radius. The uncertainty in the velocity is greater than. It is given that radius is 1 angstrom and uncertainty is given, that is 1% of the radius. Then we have to find uncertainty in velocity. We know that from Heisenberg's uncertainty principle, delta R into delta P. So uncertainty in position into uncertainty in linear momentum is h cross by 2. Here delta R, that is uncertainty in position, is 1% of the radius. Radius is 1 angstrom. That is 10 raised to minus 10 by 100. 10 raised to minus 8 meters. So delta R is 10 raised to minus 8. Delta P can be written as m into delta V equal to h cross by 2. That is 10 raised to minus 8 into mass. Mass of an electron is 9.11 into 10 raised to minus 30 into delta V is equal to h. Value of h is 6.626 into 10 raised to minus 34 divided by 2 pi. 3.142 into 2. Therefore delta V is, so after simplifying we will get 5.7 into 10 raised to 6 meter per second. Option C is answer. A system of 3 indistinguishable particles has the total energy of 4 epsilon. There are 4 single particle energy states with energy 0 epsilon, 2 epsilon and 3 epsilon. The number of microstates accessible to the system will be. Given that system contains 3 indistinguishable particles. If the particles are distinguishable, that means they obey classical statistics. But here they are indistinguishable, that means they obey quantum statistics. But there are two types. One is Fermi-Dirac statistics, second one is Bose-Einstein statistics. Fermi-Dirac statistics means they obey Pauli exclusion principle. This will not obey. In FD statistics, each state is occupied by single particle or no particle. But in Bose-Einstein statistics, there is no restriction on the number of particles. Here, given that total energy E total is 4 epsilon, number of particles are 3. Then there are 4 single particle energy states. That means, so single particle energy state means they obey Fermi-Dirac statistics. Here the number of microstates is given by W is pi I Gi C E N I, where Gi is the number of states, Ni is the number of particles. Similarly, for Bose-Einstein statistics, the number of microstates is given by pi I Gi plus Ni minus 1 C Ni. Here it is Gi factorial divided by Gi minus Ni factorial into Ni factorial. This can be written as Gi plus Ni minus 1 factorial divided by Ni factorial Gi minus 1 factorial. Since here in this question the particles obey FD statistics, the number of microstates are, here number of states are 4. 4 factorial divided by Gi minus Ni. 4 minus number of particles 3. 4 minus 3 factorial into 3 factorial. It is 4 factorial. It is 4 into 3 factorial. 1 factorial into 3 factorial. This and this cancels. Therefore, number of microstates are 4. In thermal equilibrium, at very low temperatures, the occupancy of a phonon mode of frequency omega is given by. Occupancy of phonon mode is given by n bar is equal to 1 upon e raised to h cross omega upon kBt minus 1. So you can write h cross omega upon kBt as x, for n bar is equal to 1 upon e raised to x minus 1. Then expansion of e raised to x is 1 plus x square upon 2 factorial x cube by 3 factorial, so on. When x is very small, then we'll write e raised to x is nearly equal to 1 plus x. If x is large, then e raised to x will be very much greater than 1. So here at very high temperature, since here x is inversely proportional to temperature, at very high temperature x is very small. x is very very small, then n bar can be written as 1 upon 1 plus x minus 1, that is 1 upon x is equal to kBt divided by h cross omega. As temperature increases, more and more phonons are created, that is occupancy of a phonon also increases with temperature at very high temperature. Then the second case is at very low temperature, that is e raised to x is very much greater than 1. Then n bar can be written as 1 upon e raised to x, e raised to minus x, e raised to minus h cross omega upon kBt. That is, at very low temperature, occupancy of phonon of frequency omega is e raised to minus h cross omega upon kBt. Option D is correct. Then third case is, if you consider at absolute zero, x is infinity, then n bar is given by 1 upon e raised to infinity is infinity, it is 0. Number of phonons are 0. Change in entropy of irreversible process is, we know that change in entropy is always greater than or equal to 0. So it is equal to 0 for reversible process, and in irreversible process delta S is always greater than 0. Therefore, change in entropy of irreversible process is positive. In a canonical ensemble, a system A of fixed volume is in contact with a large reservoir B. Then, in canonical ensemble, system A can exchange only energy. It will exchange energy, but there is no exchange of number of particles. In grand canonical ensemble, it will exchange both energy and number of particles. But in microcanonical ensemble, there is no exchange of energy and number of particles. So, in a canonical ensemble, A can exchange only energy with B. Which of the following quantity refers to Gibbs free energy? Gibbs free energy G is given by enthalpy H minus Ts, where enthalpy H is given by internal energy plus PV. Therefore, U plus PV minus Ts is the Gibbs free energy. Option C is correct. Specific heat of a photon gas in a black body is proportional to. So, for a black body radiation, you know that energy is directly proportional to 4 power of temperature. It is given by E is equal to Stephen's constant into T raised to 4. Then specific heat is given by dE by dt. It is 4 sigma T cube. Therefore, specific heat of a photon gas is proportional to T cube. The criterion for the application of quantum statistics is, so for quantum statistics, mean free path should be less than de Broglie wavelength. Then only we will say that they obey quantum statistics. If mean free path is greater than de Broglie wavelength, then we'll say that they obey classical statistics. The criterion for the application of quantum statistics is the de Broglie wavelength of the particle constituting the particle is greater than the mean free path. So de Broglie wavelength is greater than mean free path. Option C is correct. The Maxwell distribution of velocities at 4 different temperatures T1, T2, T3 and T4 is shown below. So here plots of molecules per unit volume versus velocity is given. 4 distribution curves are there. This is for T1, this one is for T2, this one is for T3 and this is for T4. Which of the following is true for the above diagram? A 50 Hz signal of 1 mV peak value is at the input of an op-amp based integrator. RC is equal to 1 second. The output will be. We know that an integrator always integrates the input signal. Therefore, V output is given by 1 upon RC integration 0 to T V in dt. Here RC is 1 second. So integration V in is input peak value is 1 millivolt. It is 1 into 10 raised to minus 3 dt. Therefore 10 raised to minus 3 integration of dt is t 0 to t. Therefore 10 raised to minus 3 into t, where time period t is given by 1 upon f or 1 upon 2 pi f. Therefore 10 raised to minus 3 divided by 2 into pi, 3.142 into frequency. Frequency is 50 Hz. So this will give the answer 3.2 microvolt. Therefore option B is correct. Following circuit for an ideal op-amp will work as. So in the given circuit, the input is given at the inverting terminal and we have one inductor L1 and resistor R1 connected parallel to op-amp. That means it can act as a high pass filter. Therefore option D is correct. In a nuclear counting experiment, the count rate is about 5 counts per hour. To establish the uncertainty in the count to better than 1%, you will have to count for. So given that count rate is 5 counts per hour, that means in 1 hour 5 counts. It will count 5 counts. So then after x hours it will count 5x counts. The question, so we have to get uncertainty in the count better than 1%. That means uncertainty should be better than 1%. Uncertainty is given by 1 upon root into number of counts. Should be 1%. Here if you consider after x hours, so you will get 5x counts, then uncertainty is 1%, then we can write it as root 5x 1 upon 100. That means root 5x is 100, which implies 5x is 10,000. Therefore value of x is 2000. That means to establish uncertainty in the count better than 1%, you will have to count for 2000 hours. In the following figure, the outputs are cross-coupled back to the inputs of NOR gates. Which of the following condition will lead to an unpredictable operation? So here 2 NOR gates are there and output of first NOR gate will become a input to the second NOR gate, and output of second NOR gate will become input to the first NOR gate. And we know that the truth table for NOR gates is output will be high only when both the inputs are low, otherwise output will be low. Now we consider first option, that is R is equal to 0 and S is equal to 0. So if you consider Q bar as 0 only, then QQ will give, 0 0 will give output 1. So this will go here. So 1 0 becomes 0. So from option A, Q is equal to 1, Q bar is equal to 0. So Q bar is nothing but inverse of Q, therefore that holds good. So option A is predictable. Now we will move to option B, that is R is equal to 0, S is equal to 1. So R is equal to 0, S is equal to 1. First delete this one. R is equal to 0, S is equal to 1. If you consider it again, Q bar as 0, then for this one 0 0 output is 1, then 1 will come here. For 1 1 output is 0. So from option B, Q is 1, Q bar is 0. This is also predictable. So option B is also predictable. Now we'll consider option C. Remove this one. So R is 1, S is 0. So we know that if any one of the input is high, then we will get low output. Here R has high input, therefore Q is 0 here. So 0 will come here, 0 0 will give high output. So from option C we will get Q as 0, Q bar as 1. This also holds good, therefore C is also predictable. Now we are left with last option, that is R is 1 and S is also 1. C is 1. So we know that if any one of the input is high, then we will get low output. Since here R is 1, Q is 0. Since here S is 1, Q bar is also 0. From D, Q is 0 and Q bar is also 0. This is the contradiction. So Q is equal to Q bar here, 0. This is the contradiction. Therefore this R is equal to 1 and S is equal to 1 is not predictable. Therefore option D is correct answer. The number of flip-flops required to build a mod 31 counter is, we know that, so in a counter if there are n flip-flops, then it will count 2 raised to n counts. That means a single flip-flop can count 2 counts. 2 flip-flops in a counter can count 2 square, that is 4 counts. But here it is asked mod 31 counter, that means it will count 31 counts. We know that 2 raised to 5 is 32. Therefore it requires 5 flip-flops. Option C is correct. In the op-amp circuit given below, the final output V0 T is given by. So in the circuit, So we have to find V naught T. Here we can see that this circuit is nothing but an adder. So VA with resistance R, and here it is VB. So both are given at inverting terminal. Therefore V out is given by minus RF by R1 VA plus RF by R1 VB. So here RF is a feedback resistor, its value is R. So R1 value is R only VA plus R by R, this value is also R by R VB. Therefore minus VA plus VB is the output voltage. Now we have to find VA and VB. So at this point voltage is VA. So this is the output of this circuit, that is nothing but integrator, and VB is the output of this one. Therefore VA is given by, since input is at inverting terminal, so minus 1 upon RC integration 0 to T V in with respect to dt. So minus 1 upon R value is R only, then C value is 1 upon R. So R into 1 upon R 0 to T V in. V in is Vs of t dt. Therefore minus 0 to T Vs of t dt is the VA. Now we have to find VB output at this point. So VB is given by minus RF upon R1 V in. That is RF value here is 10R. Feedback resistor is 10R divided by R1 is R only into V in is Vs of t. It is minus 10 Vs of t. Therefore V output is, so minus VA plus V, minus VA is minus 0 to T Vs of t dt minus 10 Vs of t. Therefore it is 0 to T Vs of t dt plus 10 Vs of t. Option A is correct. The critically damped series LCR circuit, where L is inductor, C is capacitor and R is resistor, which of the following is true? For series LCR circuit, the damping factor is given by, so it is nothing but a ratio of attenuation to the angular frequency. So for series LCR circuit, attenuation value is given by R upon 2L, then angular frequency is 1 upon root LC. Therefore damping factor is R upon 2L divided by 1 upon root LC, that is R upon 2L into root LC. R upon 2 root C by L is the damping factor in series LCR circuit. Then here it is mentioned that critically damped circuit. Critically damped response means it is the circuit response that decays in fastest possible time without going to oscillation. It is the response that decays in fastest time without going to oscillation. It is possible if damping factor is equal to 1. Here damping factor is R upon 2 root C by L. Therefore, it should be is equal to 1. Therefore, R square is 4 into L by C. Therefore, option A is correct.
Thanks for watching. Hope you like this video. Kindly subscribe and share this video and keep watching.